Okay. We looked at Newton's law of universal gravitation, which Newton worked out to explain the orbits of the moon and planets without using vector notation and calculus that hadn't been invented yet. In any case, he came up with the idea that this would be an inverse square law, and that's really all he needed to, that was his premise, and everything else followed, and it was a remarkably successful, completely successful theory. So why should this be an inverse square law? This is kind of a plausibility argument. Well, if you have some gravitational object here, some mass, think of a planet that is a particle-like object, meaning that at least outside the surface of the planet acts as though all its mass was concentrated at the center of that sphere, or the center of mass of this object. Okay. Think of concentric spheres around this planet. The area of a sphere is proportional to the square of its radius. It's actually 4 pi r squared, but we're just going to go with the basic idea of proportionality, that areas are generally proportional to the square of dimensions. And the dimension of this sphere, the critical dimension is the radius or the diameter, could be diameter squared. But we're going to say, okay, area is proportional r squared, which means area is some constant times r squared. Constant happens to be 4 pi. In lower variable calculus, we'll derive that when we do surface integrals next week. But in this course, we're just using the intuitive notion that areas are proportional to squares of dimensions. Of course, this requires proportional thinking, which might be a little bit of a stretch. So area is kr squared for some constant number k. Again, the constant number happens to be 4 pi. The gravitational field then is going to be a vector. A vector field could be expressed as a field in terms of your coordinate system, might be the rectangular coordinate system, might be the spherical coordinate system. Spherical coordinate system, easier to integrate, harder to do gradients and stuff. And divergences, which we haven't got to yet in lower level calculus, but will like almost right away. Okay, so we don't need multivariable calculus to understand this proportionality, understand you have a field like this. Also, the idea that the field is radial. So if we depict the field vectors at various points around a circle, they'll all be pointing toward the center, because that's where things are attracted. We're standing on the surface and we're attracted toward the center. Center is straight down from anybody, straight down from the guy here, straight down from the guy here, okay, etc. We want to talk about the flux of this field. Okay. Another aspect, well, let's talk about the flux of the field. Okay, the flux is positive or negative. Okay, the flux is, if you imagine a fluid flowing toward the center here, then the flux is a rate at which fluid flows across a given surface, this flux through that surface. So you imagine this whole sphere, and you have stuff flowing in toward the center all around the sphere. Well, the amount of stuff flowing in toward the center, if you have an incompressible fluid, water essentially being incompressible at any pressure we're likely to encounter in our lab. The amount of water flowing across the surface, if you have a steady flow, is certainly equal to the amount of water going down the drain at the center. And that's going to be also true of this surface, okay, the bigger surface. So any surface, you have the same amount of fluid flowing across it. That's flux. Flux is the amount of fluid per unit of time that flows across the surface. Now, gravity is not a fluid. The gravitational field is not a fluid, but it acts the same way. it has a flux. And the flux is obtained just by multiplying the magnitude of this vector by each little area increment and summing over the whole surface. And since all these vectors have the same magnitude because all these points are the same distance from the gravitational mass, you just multiply that constant magnitude of the field, which is magnitude of the field, and using this fancy script F for the field, multiplied by the area. Well, that's the magnitude of the flux. It's negative that if it's inward, and positive that if it's outward. The gravitation is an inward force. If you have a positive charge or negative charge, then the electrostatic attraction or repulsion, you can have an attraction or repulsion. So you can have an inward flux for something that attracts positive charges, and outward flux for something that repels positive charges. Well, we don't need to go into too much detail on that. We're going to go into plenty of detail in the spring. So in any case, for different fields, you can have inward and outward fluxes. For gravitational field, it's always inward toward the center. So the flux is always going to be negative. Okay. So if A is the area, surface area of this sphere, the flux is this. So there we have A is the area. Magnitude of F is the constant magnitude of this field. Then the flux is, narrow this. Okay, now this is multivariable calculus. Everything else I talked about really isn't multivariable calculus. It's intuitive. Anybody at the level of this physics course should be able to understand that whole idea of flux and why we multiply the constant magnitude of the field over a concentric sphere by the area. Okay, just a brief mention of the multivariable calculus. You do the double surface integral over the sphere of F dot M, and that is your flux as well. And that should be familiar to anybody in multivariable calculus at calculus 3 class at this point. So we have this statement. This is the flux on any surface where F is constant. Okay, flux is this. On any surface, make that a capital, put a period after this. On any surface where the magnitude of F is constant, and either inward or outward, and normal to the surface, which about are true here. That flux is just the field times the area, where field is magnitude of F. And we could write the plus or minus here. This is just what I wrote here, but this can be done using the concepts of calculus. Okay, well, we conclude that the total flux through any concentric sphere is this. And area of the sphere is kr squared, some multiple of r squared. It's proportional to r squared. So if the area of any sphere, surface area of any sphere, is kr squared, then it's 4 pi r squared. K would be 4 pi, but not going to worry about that. We have that then that the total flux is this. Okay, and again, the capital F without the magnitude of the arrow is just the magnitude of the field. Okay, so magnitude of the field times area is magnitude of the field times kr squared, because kr squared is the area of the surface. And the total flux is always the same because what flows through one surface eventually or quickly flows through every other surface. As it approaches the middle, it goes away. Okay, total flux is always the same. Since the total flux is always the same, then this has to equal some constant, which I'll call C. And the flux is just then, or the magnitude of the field, just C over K times 1 over R squared, reciprocal square. So we could even do a graph of the field versus R. It's just a reciprocal square graph, which everybody should be familiar with from pre-calculus. Now, that's what we have. We have this much information about the field. The field, whatever it is, we haven't really said what the field is. The field is what you multiply by a mass that we put at whatever point we're looking at on whichever concentric sphere we're looking at. If you multiply the field by the mass, you get the force exerted by the gravitational field. So we want to say then that the more mass, the more flux. Okay, because the more mass, the more attraction. If I double the mass, I'm going to get twice the attraction. It's like I've got a mass here and I get this, not put another mass on top of it. Well, then I've got the field from the first mass plus the field from the second mass, which just doubles the field. Okay. And if I've got any mass, well, it should be at least vaguely clear and become clear as we go on that the magnitude of the field is proportional to that mass. Well, if the magnitude of the field is proportional to the mass, the magnitude of the field is proportional to 1 over r squared, and specifically to c over k times 1 over r squared, then we can expand our proportionality. The field magnitude is going to be c over k times the mass. Well, c over k times 1 over r squared multiplied by the mass. Now, if you understand proportionality, that should make a lot of sense. If you don't understand proportionality, do whatever's necessary to understand proportionality. It can be understood at the pre-algebra level, but better the more sophisticated your mathematical understanding is, and the more quickly you can grasp the idea. Okay, so there's your ultimate proportionality. So now the field is gm over r squared. The magnitude of the field is gm over r squared. Okay, now what's g? It's constant. And matter of fact, if I remember correctly, its magnitude is 5.7 times 10 to the negative 11th Newton meter squared per kilogram squared. That's a universal gravitational constant, universal as far as we know. Haven't reconciled gravitational forces with all the other forces we know about. So we fully expect that particle physics is spectacularly good at predicting things, okay, at the quantum level. And then that extends to the big level. We don't need to understand too much about that. And yeah, my understanding of the quantum physics is the really big field theories is pretty modest. So I don't want to talk too much about it. Okay. It's not my field. I spent a lifetime understanding that field. I spent a lifetime trying to confuse students. Okay, so what we get out of this specifically then is that your field is gm over r squared, and the magnitude gm over r squared, where g is this. If we multiply the field now by the mass of the particle, because what the field is what you multiply by the mass of the particle to get the force. Okay. Multiplying the field by the mass of the particle gives us the force. That's what we really mean by the field. So the field is the force per unit of mass. So I have an asteroid passing the Earth. At whatever point, the field has a certain strength, and you multiply that field by the mass of the asteroid, you get the force exerted on the asteroid, which tells you how the asteroid is accelerating. You work that out to see if the asteroid is going to just be deflected by the Earth and maybe pick up some velocity from the gravitational sling effect, or maybe be slowed down, or maybe if it's not moving too fast and it's too close, maybe it gets captured by the Earth, and then you don't want to be wherever it's going to hit. And depending on the mass of the asteroid, maybe you just don't want to be anywhere. You don't want to be on the Earth because everybody's going to die. That's highly unlikely, so don't lose any sleep over it. Plenty of things that can kill you in the next 2 minutes. They're much more likely that to kill you than an asteroid within your lifetime or within 100 lifetimes. Nothing to worry about, but we do kind of want to be prepared in case we need to deflect an asteroid. And they're, I mean, like within days, one way or another, right now, I don't know if we launched the DART or not, but it's going to be launched. It's going to slam into an asteroid. And we're going to measure how it deflects the orbit of the asteroid. Very interesting thing. Okay. Digressions aside, that's what the field does. Force times mass equals field times mass gives you force. Okay, so the force then is G big M little m over R squared. It has magnitude, and it's oriented toward the center. Well, at this point, I posed the problem of figuring out the vector form of the field at a point xy. I said, okay, the hint I gave was, okay, everybody, just give me something that's radial. Give me a vector that's radial. Of course, we did this in molecular calculus yesterday. We get a radial field. People pretty quickly say, okay, it's xi plus yj. Of course, you don't want to write the I vector and the j vector for subscripts. You want to write it out this way so you don't confuse yourself later. But that was good. People got that quickly. And then did a pretty good job of sketching the thing. Well, xi plus yj, though, the original sketch, xi plus yj was this long. Well, xi plus yj is a vector from here to here. It's this long. So, respectfully kind of erased this and give you the vector xi plus yj. We want a radial inward vector. Okay, this is a radial outward vector. But if we want an inward vector, we just reverse its direction, multiply by -1. We get negative quantity xi plus yj. Now, another thing that people wrote out was this, okay, that the magnitude of this vector is square root of x squared plus y squared. That's important. Okay, so the magnitude of xi plus yj is this, which is r. Okay. So the magnitude of negative xi minus yj, well, it's still r. Magnitude of the negative is the same as the magnitude of the original vector. However, this is clearly not inverse square in nature. Okay, so we work a little bit to get the inverse square nature. Now, we put this together with the fact that the magnitude of the field is big G big M over R squared, which we got previously by just thinking about some really what should be fairly obvious proportionalities. The vector form of that vector, well, that's what we're trying to get. Okay, that's why we start with a radial vector, because the field is radial. So we get the radial vector, we get a radial inward vector, and we get the radial vector here, better written here. We get the radial inward vector, we get the magnitude of the radial inward vector, which is r. Well, that's great, it's a good start. But how do we get an inward vector that's proportional in magnitude to the reciprocal square? Okay, to the reciprocal of the square of r. This is proportional to r, not reciprocal square. Well, plugging around a little bit, people came up with this, r times gm over r. Well, that's r's divide out, that's just constant for given mass. Gm is just constant. It's Now, okay, if we then multiply this field or the opposite of the field by the reciprocal of this distance, what do we get? Well, the magnitude of this vector is r. If we divide it by r, we get a unit vector, don't we? So okay. So your I'll kind of write this out. What kind of important idea? This is a unit vector. It's constant in magnitude. So when you do this, here you're going to get something that's constant magnitude. It's not going to be reciprocal square. So, you know, comment on that. And people very quickly then, fortunately, because we're getting toward the end of the period, time is running short, said, okay, if I do r divided by r cubed, that's going to be reciprocal square. And r cubed, of course, is the cube, and wrote this out very quickly. Well done. R cubed is the cube of the magnitude of r, which is square root of x squared plus y squared. So if we take the square root of x squared plus y squared divided by the cube of the square root of x squared plus y squared and multiplied by gm, what do we get? We get gm over x squared plus y squared, because of course the algebra is real clear, which is gm over r squared, which is the magnitude of f. Okay, so bingo. Here we are now. We have an expression in terms of x and y for the magnitude of your field. We still want the vector form of the field. Well, the vector form of the field, we come back to the idea of a unit vector. Okay, so this is going to be a unit vector. It's going to be the magnitude of the field multiplied by a unit vector in the direction of the field. What's a unit vector in the direction of the field? Well, let's go back here. A unit vector in the direction of the field is a unit vector in the direction of r. There's your r vector. So it's in the direction of negative xi minus yj. And what's the unit vector in this direction? Well, it's just r divided by the magnitude of r, negative xi minus yj over magnitude, which is just negative xi minus yj over the square root of x squared plus y squared again. Now, I think maybe we wrote this down someplace. I did. I thought I wrote, yeah, okay, I wrote it down. Okay, so the unit vector in the direction of r is the r vector over the magnitude of the r vector. Again, the r vector is a vector from here to here. Divide that vector by its magnitude, now you have a unit vector in this direction. And then probably. Okay, usually the r vector goes from the origin out to the point. I did the negative of this. So I'm going to say this is in the direction of negative r. It's going to be negative r over magnitude of r. So So the unit vector in this direction is negative r over the magnitude of r, where the r vector again in this direction is the vector from the origin out to the point x, y. Okay, so there we have it. Now I just write this, except this is this. And the unit vector is negative r over r. So we just do our reciprocal square with the proportionality constant g. Multiply that by the unit vector negative r over r. And then r squared is x squared plus y squared. Negative r is negative xi minus yj. And r is the magnitude, which is the square root of x squared plus y squared. So now we have x squared plus y squared times the square root of x squared plus y squared in the denominator, giving us a 3/2 power of x squared plus y squared. That's multiplied by your negative r vector, your negative xi minus yj. And of course, we could put the negative out here, and then we have xi plus yj. And that's essentially what I've done here. You got gm over r cubed times an r vector, negative, so it's inward. I was just going to say something. I was going to say. Yeah. Now this looks like it'd be reciprocal cube, right? Portion of the cube, reciprocal cube of r, but that's not the case because the magnitude of r is r without the arrow. And so this thing has a magnitude of r. When you divide by r cubed, you get reciprocal square. And that is clearer if I write it this way. If I write it this way, it's clear this is a unit vector, so this is reciprocal square. It's just that when we work through the arithmetic, we include the magnitude of r with this instead of with this. So we're no longer identifying the unit vector, we're absorbing this here. I'm fine with this form. If you find this confusing, but you can really understand it. Okay, so that's all kind of neat. It's actually very neat, very satisfying. I'm going to extend what we did in class because that's a summary of what we did in class. I'm going to extend that now to the idea that this field is conservative. Saying gravitation is a conservative field. It is obvious in the vicinity of the Earth, the gravitation acts pretty much in just one direction toward the center of the Earth. A conservative field is path independent. If I take something from here to here and then bring it back down, it experiences the same force all the way along. Now that's great. But now what if I take it from here to here by a different path? What if I take it from here to here around some kind of a loop or even some kind of sine, okay, sine path, sinusoidal path, get it right. Is it still path independent? Is the amount of work I have to do to go from here to here equal the amount of work I have to do to go from here back down to here? Or is the amount of work I have to do to go from here to here independent of the path, which is equivalent to what I just said? So let's say that we have some path, and let's take a path along arcs of two circles. That's supposed to be a circular arc, concentric. The arc of a circle concentric with the mass. Draw it very well. If we integrate the force times our displacement, well, our forces or our fields, let's say, our field here is always radial. Okay. We just, even this directions of the field, we can see that the field does no work if we move along this arc, and it does no work if we go along this arc, because each arc is perpendicular at every point to radial line to that point. Okay, so no work is done there. Then you have these increasing forces as you move from here to here. And you have increasing forces as you move from here to here. Well, according to this law, the magnitude of F is the same. The magnitude of F depends only on how far you are from the origin. And the vector F is always directed toward the center. So that our forces along these two parts of the path, and let's say that we follow this path in the counterclockwise direction, so that we start at one point. Let's say we start here, we go from here to here, and there's no work done by the force because the force is always perpendicular to our path. So they're tangent vector force. Okay, from here to here, then, well, all these forces do positive work as we go from here to here. These forces do no work for the same reason these do. And then we go from here to here in the opposite direction. Now our path is in the direction opposite to the forces, so we do negative work from here to here. So these forces are identical at every distance from the center to these forces, but we're moving in the opposite direction. So it's fairly easy to see that we do zero work as we go around this path. Okay, so we're path independent on a path like this, but what if we have a more complicated path? We go start here, go around here counterclockwise and come back to here. You can't make the simple argument here. In this case, you use a fundamental theorem of vector calculus, which says that if F, maybe fancy there, I'm losing my F's now, of say X, Y, Z, whatever coordinate system is the gradient for some function F, then F is conservative. Path independent in the sense that the integral around any closed path has to give you zero. Okay. Well, here's F. Is this field a gradient of some potential field? Turns out man, I can't write what I want you to write. Turns out to be true. if f of x, y, z is this. Okay, now I've all of a sudden gone to 3 dimensions here. But this law in 3 dimensions, you're just going to have an x squared plus y squared plus z squared here. And here, and here. Still going to have the same form. Okay. If you take the gradient of this, you got to get this. And this is called the potential function. I have to use your more variable calculus. You have to know how to do the gradient of this, and which is fairly straightforward. But there it is. I might be off by a constant in that thing. I don't think so. But until I work it out, I'm not absolutely sure I did this right. We can say that though the derivative with respect to r of 1 over r is negative 1 over r squared. In the same sense, the derivative of this r, in whatever direction, should be negative 1 over r squared. And that makes this very plausible. Okay, more about this. You can work it out. You can do the gradient there. You can check it out. If the gradient isn't equal to this, we have to do that expression to make the gradient equal to this. Again, I haven't proven that to myself, so I'm saying it with a little bit of reservation.